Okay, we've got rules for logarithms. One rule is log of A plus log of B is a log of A times B. This is inverse to the law of exponents. X to the A, x to the B equals x to the A plus B. Okay, we have a multiplication giving us an addition here. We have a multiplication here giving us an addition here. Now it's an inverse relationship, but I'll let you puzzle over what that means. Make sure you understand the law and hopefully how it compares and contrasts with this law of exponents. Okay, you also have B log of A is a log of A raised to the B power, which is related to the law of exponents where you have a power raised to a power. Okay, you have a product here giving you a power here. Here you have a product giving you a power. You might want to ponder that. And then this pretty much redundant thing, log of A minus log of B is a log of A divided by B, which comes about just by combining these two. But in any case, it's related to this law of exponents. So for example then, log of P plus 3 log of 7. Okay, how do we simplify that? Well, we're going to do the multiplication before the addition, kind of like we do with the order of operations, because we don't have a rule that allows us to combine the addition of multiples of logs. The rule here only applies to logs. If you've got a number in front of one of the logs, you've got to do this first. Okay, so we have the 3 log of 7, that's log of 7 to the third by the second rule. And then we have an addition of 2 logs, so we can express that as a log of the product of those two quantities. And then, if we want, we can raise our 7 to the third power, that's 343. But there's the result. Now, we often apply logarithms to solving exponential equations. And we have a couple of rules that are important. This one that might have been included over here. Log to the base B of A is a log of A divided by the log of B. And also the fact that, and this is actually fundamental, this actually comes before everything else, log base B of A equals C is equivalent to saying B to the C equals A. So, especially if C contains the variable you're trying to solve an equation for, you can't get to it when it's in the exponent. You can change it to log form, and then if your variable's in C, well, here it is where you can just use standard algebra on it, hopefully. Okay, so we're going to solve this equation. 40 times 1.07 raised to the x equals 60. We want to put this equation, if possible, into the form b to the c equals a, because our x, the variable we're trying to solve for, is in the exponent. So we're going to try to put the equation into this form. That's easily done. We divide both sides by 40, and we get 1.07 to the x equals 60 over 40. So 1.07 to the x is 1.5. Now that's in the form b to the c equals a. So that's b to the c equals a, with b equal to 1.07, c equal to x, a equal to 1.5. Having identified that, we can say, well, it follows that this is equivalent to log base b of a equals c with these values of a, b, and c. So we take b equals 1.07, and b log base b becomes log base 1.07. A is 1.5, so A is going to be 1.5 equals C, well that's x. So we get x equals log base 1.07 and 1.5, and then we use this rule, and we get x equals log of 1.5 divided by log of 1.07, which you can put into your calculator. Okay, a couple more examples. I'm going to solve 1,000 times 1.03 to the x equals 2,000. That is, for example, if you have $1,000 at 3% interest compounded annually, then after X years, you're going to have this much money. And you want to find out when you're going to double your money, when you're going to be up to $2,000. So, and I rewrote it because the thing was off the board, or we had to do some things with the board. But it's just rewritten here. We divide both sides by 1,000, we get 1.03 to the x equals 2. Well, that's in the form b to the c equals a. B is your base, that's your 1.03. C is your exponent, and a is 2. So b is 1.03, c is x, a is 2. That's equivalent to this form. So we write this form with these values of a, b, and c, and we get log base 1.03 of 2 equals x, so that x is log of 2 over log of 1.03. It's approximately 24. Another example, 4 to the 3x minus 5 equals 7. Equation we want to solve. Again, we see that our variable's in the exponent, making this an exponential equation. We want to convert it to a logarithmic equation, so we see this is in the form b to the c equals a, b to the c equals a. We identify b here, we identify c here, and we identify a over here. And then we rewrite in logarithmic form, and it's going to be log to the base b, log base 4 of a, 7 equals c, which is your 3x minus 5. And now we just do the standard algebra. And it's possible to evaluate this approximately, but let's just keep it in its exact form for now, because it's actually kind of easier in writing out the numbers. So 3x minus 5, we add 5 to both sides, we get this. And then we want to find x, we divide both sides by 3, and here we have it. And then we write log base 4 of 7 as log 7 over log 4. And then we have the plus 5 over the 3. And now it's in a form where you can put the whole thing into your calculator. And I think you get something between 2.1 and 2.2. And I estimated 2.17. That's high. Should be more like 2.12, something like that. Hard to estimate this. This is a little bit high, but you can plug it into your calculator and you're going to get the result.